All right, so here's number 3, the one with the person kicking the ball over the fence, or hopefully over the fence. So in the problem, he kicks the ball at 20 meters per second. You have some stuff about the kick in the problem, but it also gives you up there approximate values of sine and cosine and tangent of 37. It's really 37 point something. It's for a 3, 4, 5 right triangle. So when they do things like this, it's to make the math easier, so that you need less help with the calculator. Like, this is the type of problem you could do a lot of it without a calculator. They're not expecting you to be using a fancy graphing calculator. So it looks like it's trying to go over the fence. We have this thing where he's kicking the ball. And if you go back and you remember when we were talking about like somebody kicking something or hitting something or doing things like that, we use the concepts of impulse and momentum. That's one way to do it. You can also do it simply with force as well. And then after that, it's projectile motion. So the same thing we've done before. The horizontal motion is constant. The vertical velocity is accelerated. So we'll look at how that works. So for 3A, it asks, how much force does he average? What's the magnitude of the average force? Remember, magnitude just means the number without a direction, usually like the absolute value. And then the average force just means it's going to kind of change a little bit over the time, but we're going to look at that. That means we can just use any of our delta equations, and it's fine. We don't need to take a derivative or anything crazy like that. So I use the definition of impulse, where it's force is change in momentum over time. You could also do mass times acceleration is m delta v over delta t, because it asks what is the net force. So plugging in all of that same stuff, so mass times velocity is momentum, or mass times change in velocity over time is acceleration. And so I put those together and get 200 newtons is the average force that he applies there. So then it asks, so over the first 0.05 seconds, it's doing that. So then in that point, it's firing along at that 200 newtons. But now it's asking us, how long does it take till it gets to the plane of the fence? How long does it get there? And so we use the horizontal speed, because that's what's important. We know that the horizontal speed is just the hypotenuse times the cosine of the angle, so that's 16 meters per second. We also know that distance is velocity times time, and it's constant velocity because it's the horizontal component. So we can rearrange that or just solve with basic stuff. It's going 16 meters per second, and it's going 32 meters. It takes 2 seconds. So that's how long it would take to get to the fence. Now, to see if it actually clears the fence, we need to see how high it's going to be after those 2 seconds. So we plug in our equations with accelerated motion. We know in the vertical direction it's going v0 sine 37, which is 12 meters per second, because it's 20 times 0.6, and then minus 1/2 gt squared. So if you plug that in, I get a height of 4.4 meters. So the answer would be, if the fence is 2.5 meters high, it would clear by about 1.9 meters. So then it's asking, to graph the velocity of the horizontal and vertical components. So I decided to do that once again. Nice thing, the horizontal velocity is constant at 16. Now, if you look at each of these, so like this would be 0.5, this would be 0.1. So it turns out it started at 0, but he kicks it in 0.05 seconds. Now, on my graph here, so this would be 0.1, so 0.05 is half of that first tick. So I go to 16 here. So it goes very quickly up, but then it goes straight across for 2 seconds. Now it's probably going to go farther than that, but we only worry about until it hits the fence. I think that's all until it clears the fence. The vertical component does something fairly similar. It starts at 0, and then it gets up to 12 in 0.05 seconds. So very, very quickly goes up. Now, if you skip that first part, I don't think they're going to do anything too much to you there. But what happens is it drops by about 9.8 meters per second each second. And so in 1 second, it goes from 12 to about 3 and then goes down. It crosses at about 1.2 seconds. And so it goes like that. So the vertical component of velocity starts out positive because it's going up, but then it starts to go back down. So your graphs should look like that. They're not too complicated. You just need to remember how the graphs are related to what you're trying to do.